Y25 photon. The energy momentum relation in relativity is energy divided by the speed of light of a particle whose rest mass is m0 is like that. If the rest mass is non-zero, in that case, there exists a frame of reference in which a particle is at rest. Therefore, in the rest frame, the energy of a particle is m0c squared. However, in the case of a photon, it is traveling with the speed of light, so there is only a single constraint that m0, the rest mass of a photon, must be zero. If it is non-zero, there must be a rest frame, but there is no rest frame for a photon because the electromagnetic wave is always traveling with the speed of light. Therefore, if we substitute the rest mass m0 equals 0 in this formula, then we arrive at the relation. The energy of a photon is proportional to the momentum of a photon. And using this result and the result of a photoelectric effect that derives energy is proportional to the frequency, we can find a very, very important formula. Okay, first of all, 1905, Einstein proposed that the energy of a photon is a single photon is proportional to the frequency. Here, the frequency is 1 over period. Okay, so if we multiply 2 pi, it becomes 2 pi nu and angular frequency. In addition, this is called the Planck constant, and the Planck constant can be divided by 2 pi. In that case, we call it reduced Planck constant. Therefore, h nu is h over 2 pi and 2 pi over period. And this one can also be written h bar times omega. By the way, photon is being emitted from such as matter. Electrons are usually trapped by an atom. For example, a proton and electron system, this bound system is called hydrogen. And if you hit this electron by, for example, using a photon, if this photon has an energy large enough, then the hit electron is being emitted. Okay, so the energy of the photon is closely related to the bondage between the electron and proton. When the kinetic energy of photon is large enough, then this bondage is broken and electron can be emitted. That is the photoelectric effect. If you look at the experimental result at the time when the photoelectric effect was detected, people knew about the Rydberg constant. That is related to the energy of a photon and actually the wavelength. At that time, there was no information about the energy. The Hydrogen atom is a bound state of proton and electron, and hydrogen can emit electromagnetic radiation, and its wavelength was found to be quantized. That means 1 over wavelength is a constant multiplied by the difference of 1 over integer squared. Here, these integers are positive integers that runs from 1 to infinity. But let us concentrate on the smallest numbers. And people detected the spectra of a hydrogen atom, and that was not continuous like the white light coming from the sun. Instead, they are quantized. The line spectrum has been detected. So people wanted to understand that this discrete spectrum, the why the electrons, because the radiation of photon, if we consider the energy conservation of the whole system, it seems that after radiating a photon, then electron loses energy, and it goes down to the further down, closer to the proton. If electromagnetic field is absorbed by an electron, it will be excited to higher energy state. And if the energy of the incident photon is large enough, the bondage will be broken and electron can be emitted, something like that. Anyway, this emission and absorption process, the energy level of an electron proton system seems to be quantized, not continuous. And it was tested by making use of incident electromagnetic wave on the surface of a matter, and the result is that electrons are emitted from the metal surface. However, emissions happen only if the wavelength of this incident light should be shorter than a certain value. That is a kind of threshold. So it seems to me the wavelength determines a kind of energy of the electromagnetic wave. If you look at the experiment more closely, the emitted electron due to radiation, this incident electromagnetic wave with wavelengths shorter than a threshold value lambda 0, photoelectrons are emitted, and we can make use of the varying the resistance of this circuit. We can change the potential between this and the remaining part. You can see there is a target, and after electromagnetic field hits this target, photoelectrons are being emitted, and in case its energy is large enough, it has some kinetic energy of an electron, and by charging this plate with negatively charged particles, that is potential is lower than this. So this potential is lower. In that case, emitted electron usually collected on this part collector, but if we increase the potential, electron stop accumulating on the surface. So that is called V-stop. By applying a potential difference, we can stop collecting the photoelectrons by a collector. So this V-stop determines the maximum value of the kinetic energy of photoelectrons. Photoelectrons are emitted electrons in the photoelectric effect. Okay, YK max, it is the direction can be randomly distributed because the hitting we cannot really control the exact direction or direction of the radiating field and the direction of these targets. Therefore, this V-stop determines the maximum value of the kinetic energy of photoelectrons. By the way, the electrons were trapped by atoms on the surface of the matter, and after the hit by a photon, it acquires kinetic energy. But there should be some energy to be spent to break the bondage of the electron with atom. That is called work function. That is the kind of potential energy between the electron-atom system. Okay, so this one is treated to be the threshold energy required to break the bondage. That depends on the structure of atom. And this one is a frequency. So frequency is the speed of light divided by the wavelength. So threshold frequency is related to the threshold wavelength. Einstein introduced this following idea. Energy of an electromagnetic field is not proportional to the intensity. The energy is for a single photon instead of we remember that the Poynting vector is a speed of light multiplied by the energy density. So this was a Poynting vector. And the unit direction vector. So there is no constraint that the wavelength or frequency enters here, because Maxwell's theory states that the energy density of the electromagnetic wave is a 1/2 electric field square and plus 1/2 permeability constant magnetic field square. So there is no information about the wavelength or frequency. Because there is a threshold of frequency or wavelength only for the value of the wavelength shorter than lambda 0, and only for the incident electromagnetic wave greater than this threshold nu 0, photoelectrons were emitted. So Einstein proposed that this energy of an electromagnetic field is transferred to the electron through a single particle that is called photon. And a single photon has a certain energy that is h nu. Okay, so when the energy is greater than this axis is frequency, frequency should be greater than this is threshold value. And from then on, the kinetic energy, maximum kinetic energy of the electron is obtained by subtracting this amount of energy that is required to break the bondage between the energy is transferred to the electron to break the bondage with the atom that is called work function. So this one is experimentally measured with the E times electron charge, magnitude of the electron charge multiplied by stopping voltage, and this work function is determined by this threshold frequency or threshold wavelength. If you extend this line to the y-axis of v-stop, we arrive at a y-intercept that is exactly the same as a phi over e. So this one determines, this point, y-intercept determines the work function. And the slope determines the natural constant called Planck constant that determines the energy of a photon. If you look at this plot for the v-stop, you will find, extend this line, and here you will find that the intercept, the magnitude of the y-intercept increases as lithium 3, what's that? Atomic number. As atomic number decreases, this work function increases. Okay, so you can find that this is a small and it increases as the atomic number decreases. So I told you the phi, the work function phi, determines the energy scale of the binding energy between the electron and atom. And you know, the size of lithium is much, much smaller than the size of cesium. So the distance between, average distance between the nucleus and the electron, the positively charged particles, the distance, you know, the electrostatic potential is proportional to 1 over r, magnitude is. So if it is far than the energy scale, the strength of this binding force is smaller than the strength of the binding force between the two that is very near. So as a result, photoelectric effect has shown that the energy of an electromagnetic field is actually carried by single particles, and each particle is called photon, and energy of a single photon is frequency multiplied by a natural constant called Planck constant. And if you consider the rest mass of a photon, it should be 0. And from this relation, you find that energy of a single photon is proportional to the magnitude of momentum. if we combine these two formulas, and here we arrive at a very interesting result. The momentum is proportional to anti-proportional to the wavelength. That means particle has a wave nature whose wavelength is reciprocal to the momentum. It will be extended to other particles other than photon, for example, electron, and that is the beginning of the quantum mechanics. After the photoelectric effect that measure the work function, the binding energy of an electron trapped to an atom, people used more increase the energy of the incident electromagnetic field. And for example, X-ray is has the shorter wavelength, and using this large momentum or large energy incident photon, they studied the relativistic nature of electron too. So in here, photoelectric effect, the kinetic energy of for photoelectron can be treated as a non-relativistic momentum, the kinetic energy. However, by increasing the energy of an incident electromagnetic field, the photon, we were able to test this really relativistic behavior of electron. That is called Compton scattering. And Compton scattering, you can review all of the constants. Compton scattering is written in here. Photon comes in, and there was an electron and that is trapped by an atom, but this photon's energy is very large, so k vector multiplied by the speed of light is the incident energy of this electromagnetic field called photon. If it is very large in comparison with the work function, so we can ignore the work function, the binding energy. In case this is much greater than 5. In that case, even though we allow incident electromagnetic wave on a matter surface, electron, both the electron and the radiated photon can be detected in this experiment. And the electron's kinetic energy is not 1/2 mv squared anymore, and we can really test the kinetic energy. We remember gamma minus 1 m0c squared is the relativistic kinetic energy of a massive particle, and this formula has been really tested. And you can see this photon and this photon. This is incident photon, and this is a scattered photon. This is the energy of this incident photon is shared by these two particles. Therefore, this scattered photon is less energetic. Less energetic means the wavelength of the scattered photon must be longer than that of the incident photon. This plot shows that lambda prime is significantly greater than the original incident photon. Compton scattering, Compton wavelength is defined in such a manner. So energy of a particle is can be scaled by this Compton wavelength, and if the energy of a particle has the wavelength of the scale of Compton wavelength, then it will show relativistic behavior. For example, when the energy is comparable to the Compton wavelength, in that case, we cannot make use of non-relativistic kinematics. For example, 1/2 mv squared cannot be used in that energy scale. So explicit calculation for the Compton scattering can be done with these four vectors. Four vector is for momentum of a target electron. It used to be at rest. The target was at rest. So free momentum is exactly 0. And the time component is mc squared divided by speed of light. So rest mass multiplied by the speed of light. Okay. After being hit by this incident photon, we remember photon has a rest mass 0. So energy of a photon must be the free momentum multiplied by the speed of light, and it should be divided. So this value is the energy of an incident photon divided by the speed of light. We align the momentum of the incident photon along the x-axis, so magnitude multiplied by unit vector. After this collision, both photon and electron are scattered. Scattered photons have the same structure but different momentum. And the direction is also different. Again, we can consider the relativistic form momentum of a scattered electron. The target electron was at rest. By the way, the scattered electron is moving with the momentum. Therefore, its energy divided by the speed of light is written in this form. And both electron and photon that are scattered are used prime. This angle relative to the x-axis is phi 4.5, and this one is theta. Therefore, the scalar product between the two unit vectors is cosine phi, and this one is cosine theta. Einstein's form momentum conservation is sum of energy in the initial state should be the same as sum of the energies in the final state. Again, linear momentum conservation is also true. Sum of these two vectors must be the same as sum of these two vectors. The relation is given like that. This is energy conservation, and this is momentum conservation. So sum of these four momentum in the initial state and sum of these momentum for the final state gives both the energy conservation and linear momentum conservation. And we know how to compute the scalar product between the two unit, among these three unit vectors. We can simplify this relation using square this subtracted by this square of this. And if you square this, we know square. The reason why we know a full momentum P is a P0 and the spatial components and this one is invariant on the Lorentz transformation. So we make use of this expression and use these constraints. We can simplify this relation to arrive at the angle phi. Phi is the scattering angle of a scattered photon, and the result shows that it is 1 over magnitude of momentum. You know, the magnitude of the scattered electron's momentum is always smaller than the incident electron's momentum. So smaller 1 over smaller value subtracted by a 1 over larger value must be positive definite. So the wavelength of the scattered electron is always longer than that of the incident photon, not electron, but photon. Therefore, it is called this shift in the wavelength, or the Compton scattering is a scattered photon in comparison with the incident photon gives this formula. This is useful. It confirms the experimental fact, but this is not the most important one. The most important one is that for momentum expression that was developed by Einstein was completely confirmed in this experiment. So Compton scattering, due to both the photoelectric effect and Compton scattering, Einstein's relativity was completely proved by experiment.